Of all the questions we can ask about existence, perhaps the most profound is also the most unsettling. Why is there something rather than nothing? Why do you exist? Why does anyone? Why does the world, with all its beauty and brutality, its complexity and contradiction, persist at all? From the molecules in your breath to the vast galaxies spinning silently in the cosmic dark. Why are any of these things here? According to our best understanding of physics, they shouldn't be. The universe itself, its stars, its silence, its laws, and its life should never have been born. To begin unraveling this paradox, we must return to the very first instant, the birth of everything, the Big Bang. It was not merely an explosion of matter, but of space-time itself, a singular event of unimaginable energy and baffling precision. The odds that such an ordered cosmos could emerge from primordial chaos were not simply slim, they were vanishingly small. British physicist Sir Roger Penrose attempted to capture just how improbable this beginning was. His estimate, a number so staggeringly huge it defies intuition, has come to be known as the Penrose number 1 in 10 to the 10 to the 123. That is a 1 followed by more zeros than the number of atoms in the observable universe, a number so extreme that calling it impossible barely does justice to its scale. It speaks to a universe birthed not in chaos, but in breathtaking coherence, like a cosmic sculpture chiseled with infinite precision. This low-entropy beginning is deeply mysterious. As time flows forward, systems tend toward disorder. It's the arrow of time. Entropy increases and order decays. We see it in the slow ruin of ancient cities and the fraying of our own bodies in the tangled knots of headphone wires left in a drawer. We expect the same of the cosmos. Black holes, as Penrose noted, are the ultimate endpoints of this decay, the graveyards of structure where complexity collapses into featureless oblivion. Yet here we are, nearly 14 billion years after the beginning, still surrounded by intricate structures, by stars, by minds, by the astonishing dance of life and matter. The universe remains astonishingly ordered. And entropy is not our only puzzle. We live in a world dominated by matter, by the particles that make up you, me, the Earth, and the stars. But every particle of matter has an opposite antimatter. And when matter meets antimatter, they annihilate each other in a flash of pure energy. So, where is all the antimatter? Why did just enough matter survive the primordial inferno to build a cosmos when our equations suggest symmetry should have ruled equal parts matter and antimatter destined to destroy each other completely? Nothing should remain. Not a single atom. And yet, improbably, something did. Then, perhaps most baffling of all, comes the issue of weight. Not of stars or galaxies, but of space itself. Quantum theory tells us that even in a perfect vacuum, energy bubbles and boils into existence. These fluctuations give empty space a weight, one that, when calculated using our best understanding of quantum fields, is staggeringly high. So high, in fact, that the moment the universe sprang into being, it should have curled back in on itself and vanished. It should have been crushed by the weight of its own emptiness. Instead, the universe expanded. Space stretched. Light emerged. Galaxies formed. The cosmos lived. This vast mismatch between theory and observation is known as the cosmological constant problem, and it haunts modern physics. It is not a subtle discrepancy. It is a chasm between the predictions of our models and the reality we observe. It tells us that something fundamental is missing in our understanding, something hidden deep in the structure of the vacuum itself. And so we are left with a troubling truth. We should not be here. Not because of a failure of imagination, but because of a failure of explanation. The universe is not just improbable, it is by all accounts impossible. And yet impossibly it is here, and so are we. What is energy? At first glance, it seems a straightforward question. Yet, beneath its surface lies one of the most profound concepts in physics, an idea that binds together the functioning of stars, the breath in our lungs, the technology we use, and even the mass of the cosmos itself. Energy is not a single entity, but a unifying thread connecting diverse processes and phenomena, from the combustion of fuel in a locomotive to the fusion of hydrogen in the heart of the sun. But understanding how we came to see it this way requires a journey not through equations, but through observation and insight, beginning with an unlikely figure aboard a 19th century sailing vessel. Julius Robert von Meyer, a ship's doctor sailing through the Dutch East Indies in the 1840s, was struck by an unusual detail. Treating sailors in the tropical heat, he noticed that the color of venous blood, the blood returning to the heart, was brighter than expected. In colder climates, such blood would appear darker, depleted of oxygen after fueling the internal combustion that keeps our bodies warm. But in the suffocating heat of the tropics, the sailors' bodies didn't need to burn as much food for warmth. Their metabolism slowed and less oxygen was consumed. The blood returning to the heart was nearly as red as when it left the lungs. This small biological observation led von Meyer to a remarkable conclusion. The energy that the body normally produces through metabolism was being supplemented by the heat of the surrounding environment. In short, heat and biological work were interchangeable. He had glimpsed a universal principle. Energy may take many forms, but it is conserved and convertible. By the mid-19th century, such ideas were beginning to coalesce into a broader framework. Scientists realized that energy could be stored, transferred and transformed, whether in the potential energy of a suspended weight, the chemical bonds of coal, or the expanding steam that powered industrial machinery. Energy, in essence, was capacity. The capacity to do work. And work in physics is the application of a force across a distance. These foundational insights prepared the stage for the 20th century, when energy would be redefined yet again, this time in the most unexpected place, in the very mass of objects. Albert Einstein's theory of special relativity, published in 1905, did more than upend our notions of space and time. It also transformed our understanding of inertia. Imagine a hypothetical scenario where an idealized human, a supercharged Usain Bolt, could be accelerated to near the speed of light. To push him faster and faster, more energy would need to be fed into the system. Yet, as his velocity approached the universal limit, his resistance to further acceleration would increase. This resistance is not arbitrary. It is inertia. And what Einstein saw was that the energy being added wasn't disappearing. It was manifesting as growing inertia. And inertia is another word for mass. In a moment of sublime clarity, Einstein saw that mass and energy are two expressions of the same fundamental thing. And this insight he captured with his most iconic formula, E equals mc2. The implications of this are profound. It tells us that even at rest, an object contains an immense amount of energy. The c in that equation, the speed of light squared, is a massive multiplier. A modest 9-kilogram object, like a small dog, contains energy equivalent to 200 megatons of TNT. This is not just theory. This mass-to-energy conversion powers nuclear weapons and fusion reactors. In both, mass is transmuted into heat, light, and kinetic energy. And in the cores of stars, including our Sun, this process sustains the very existence of life on Earth. Hydrogen nuclei fuse into helium, releasing energy as they lose tiny amounts of mass. The difference is minute but multiplied across a star's lifetime. It becomes monumental. Einstein's revelation also changed the way we think about gravity. In Newton's formulation, gravity pulled on mass. But Einstein, having unified mass and energy, realized that gravity must pull on energy as well. Light, though massless, is bent by gravity because it carries energy. This is not a metaphor. It is a measurable, observable phenomenon. Light from distant stars is deflected as it passes near massive bodies, an effect confirmed during the solar eclipse of 1919 and now seen routinely in the lensing of galaxies. So when physicists ask how much something weighs, they are not concerned solely with its mass. They are asking about its total energy content. This includes not just the rest mass of the object, but also its kinetic energy, its internal energy, and even the energy contained in the space around it. The universe therefore has a weight, and that weight is determined not only by the visible matter star's gas dust, but also by radiation kinetic motion, and most mysteriously the vacuum itself. This brings us to the heart of modern cosmology. The mass-energy content of the universe is the source of its gravitational behavior, and when we survey the cosmos, we see a surprising pattern. The visible matter accounts for a mere fraction of the total energy budget, roughly 5%. Dark matter, an unseen but gravitationally active substance, accounts for another 25%. The remaining 70% is something stranger still: dark energy, an invisible component permeating empty space and driving the accelerated expansion of the universe. This is where the concept of energy becomes most enigmatic. The vacuum, seemingly empty, is not truly void. Quantum field theory tells us that even in the absence of particles, energy remains. Virtual particles pop in and out of existence, borrowing energy on short timescales in accordance with the uncertainty principle. But this vacuum energy carries weight, and gravity responds to it. The cosmological constant, Einstein's term for the energy density of the vacuum, exerts a repulsive force, causing space itself to expand. When physicists attempt to calculate this vacuum energy using quantum theory, they arrive at a catastrophic number, many orders of magnitude higher than what is observed. The difference between theory and reality is one of the greatest in all of science. This is the cosmological constant problem. The energy of the vacuum should be so immense that the universe would have torn itself apart at birth, and yet it did not. Something is missing in our understanding, some piece of the puzzle not yet found. So, what is energy? It is heat and light motion and mass radiation and gravity. It powers stars and sustains life, and it defines the weight of the universe itself. From the biological insight of a 19th century physician to the relativistic revolutions of the 20th century, our conception of energy has evolved into something profound and mysterious. As we turn our instruments to the skies and attempt to weigh the cosmos, we are not just measuring mass. We are measuring the energy of everything: the visible, the invisible, and perhaps the unknowable. How much does the universe weigh? In the 3rd century BCE, in the city of Syracuse, the great mathematician Archimedes turned his mind toward a question that, though deceptively simple in phrasing, demands the loftiest intellectual tools to address how many grains of sand could fit inside the cosmos. In his treatise, known as the Sand Reckoner, Archimedes dismissed the notion that the quantity of sand in the universe was infinite, and instead set out to calculate a number one anchored in tangible, measurable quantities, beginning with the width of a poppy seed and extrapolating to the entire celestial sphere. This endeavor led him to construct an entirely new numerical system, and by estimating the universe to be a sphere centered on the sun and bounded by the fixed stars, he concluded that it would contain no more than 163 grains of sand. The estimate, astonishingly close to modern conceptions of the universe's mass-energy content, was of course a numerical coincidence, since Archimedes was constrained by the astronomical knowledge of his day. Nonetheless, his desire to quantify the cosmos laid conceptual groundwork that resonates even now. Today, we no longer speak in terms of poppy seeds and grains of sand, but in terms of energy mass, space-time curvature, and quantum fields. When cosmologists ask how much the universe weighs, they are not weighing celestial bodies with scales, nor are they tallying particles one by one. Instead, they are evaluating how much total energy exists within the observable universe, and how that energy in all its various forms distorts the fabric of space-time. This, in essence, is the weight of the universe, not a weight in the Newtonian sense, but a measure of the energy content that governs the gravitational dynamics of the cosmos. To estimate such a quantity, one must first delineate what is meant by the universe. More precisely, scientists focus on the observable universe, that portion of the cosmos from which light has had time to reach us since the Big Bang, roughly 138 billion years ago. One might initially suppose that this corresponds to a sphere 138 billion light-years in radius, but that would be an oversimplification. Due to the expansion of space over cosmic time, the most distant galaxies we can observe today are actually around 465 billion light-years away. This defines the radius of our observable universe, making its diameter nearly 93 billion light-years. This sphere encompasses all that we can potentially observe, but not necessarily all that exists. Beyond its horizon may lie further galaxies, further structures, perhaps even regions governed by different laws of physics. We simply do not and cannot know. For our purposes, however, we restrict ourselves to the observable universe, and within that finite yet vast domain, we attempt to sum up the total energy content. We begin with stars. The Sun. An average-sized star has a mass of approximately 2 × 1030 kilograms. The Milky Way galaxy contains an estimated 100 to 400 billion stars, amounting to a stellar mass of about 1042 kilograms. There are at least 200 billion galaxies in the observable universe, each containing roughly 100 billion stars, suggesting the total stellar mass is approximately 2 × 1052 kilograms. This is already an enormous figure, but it accounts only for the luminous material stars and perhaps planets and visible interstellar gas. However, much of the universe's matter is not luminous. A more precise measurement comes from analyzing the effects of matter and energy on the geometry of the universe itself. One of the most powerful tools for doing so is the study of the cosmic microwave background radiation, or CMB, the afterglow of the Big Bang, now cooled to just 27 Kelvin. This ancient radiation carries with it the imprints of the universe's earliest fluctuations in temperature and density fluctuations that seeded the formation of galaxies and large-scale structure. Using data from satellites such as COBE, WMAP, and Planck, cosmologists have measured minute temperature variations in the CMB across the sky, and from the statistical properties of these variations inferred the density and composition of the universe with remarkable precision. From these measurements, we now estimate the total mass energy content of the observable universe to be approximately 15 × 1053 kilograms. This includes not only the visible stars and gas, but also all matter, baryonic and non-baryonic, and radiation. And when we convert this mass into energy using Einstein's famous relation E equals mc2, we find the equivalent of about 135 × 70 joules of energy. It is an incomprehensibly vast reservoir, yet it represents only a small fraction of what the universe actually contains. That is because the visible matter, the atoms that compose stars, planets, and people, accounts for only about 5% of the universe's total energy content. The rest is composed of two enigmatic components: dark matter and dark energy. Dark matter is a form of matter that does not emit, absorb, or reflect light. It interacts gravitationally but not electromagnetically, making it invisible to our instruments. Its existence is inferred from its gravitational effects on the rotation of galaxies, the dynamics of galaxy clusters, and the bending of light from distant sources via gravitational lensing. Dark matter comprises about 27% of the universe's energy budget. Yet, even dark matter is not the dominant component. That distinction belongs to dark energy, an even more mysterious substance that constitutes roughly 68% of the total. Unlike dark matter, which pulls structures together through gravity, dark energy is responsible for the accelerated expansion of the universe. Its effects were first observed in the 1990s through studies of distant Type Ia supernovae, which appeared dimmer than expected, suggesting that the rate of cosmic expansion had increased rather than slowed over time. Dark energy behaves differently from all other forms of matter and radiation. It has an energy density that remains constant as the universe expands. This is deeply counterintuitive. Ordinary matter becomes more dilute as the universe stretches. So does radiation, whose energy per photon also diminishes, but dark energy remains the same per unit volume. This implies that as space expands, new dark energy is created, a bizarre but consistent consequence of general relativity when applied to a vacuum with energy. This vacuum energy, referred to variously as the cosmological constant, the zero-point energy, or the vacuum expectation value, permeates all of space. Quantum field theory tells us that even in a perfect vacuum where no particles exist, quantum fields are never truly at rest. They fluctuate constantly, creating short-lived virtual particles that emerge and vanish in a seething quantum froth. These fluctuations contribute energy to empty space, and that energy gravitates. It bends space-time just like mass does. This vacuum energy, according to quantum theory, should be enormous. So enormous, in fact, that it would have curved the universe into oblivion in a fraction of a second after the Big Bang. This brings us to one of the most profound problems in modern theoretical physics: the cosmological constant problem. The discrepancy between the predicted and observed values of the vacuum energy is not merely large, it is the largest known disagreement between theory and observation in all of science. Quantum field theory predicts a vacuum energy density that is 120 times greater than the observed value. This is a number so large that it defies imagination. It suggests that if the vacuum energy were truly as predicted, the universe would have imploded almost immediately after its creation. No stars, no galaxies, no structure, certainly no life would ever have formed. And yet, here we are. The vacuum. Energy, for reasons no theory currently explains, is small. Astonishingly small, yet non-zero. It is precisely the right magnitude to allow for a universe that grows slowly over billions of years. A universe that permits the emergence of complexity biology and consciousness. This apparent fine-tuning of the cosmological constant remains one of the greatest mysteries in cosmology. It suggests either an underlying principle yet to be discovered, or perhaps a selection effect in a multiverse scenario where many universes exist, each with different vacuum energies, and we find ourselves in one of the rare few where conditions are right for life to emerge. In total, when dark energy is included, the full energy of the observable universe converted into the TNT equivalent to illustrate its staggering scale amounts to approximately 67 × 10⁵ kilograms of mass energy, or roughly 60 × 10�71 joules. But this energy, vast as it is spread thinly across the immense volume of space. The average energy density of the universe is incredibly low, less than a few hydrogen atoms per cubic meter, and dark energy even more diffuse. A coffee cup filled with vacuum energy contains less energy than the kinetic energy of a falling mosquito. It is only because space is so vast that these small quantities add up to such a significant gravitational influence. And so, in the final reckoning, our universe is not massive because it is densely packed with material, but because it is so vast. Its weight in the sense of total energy emerges from the product of low density and enormous volume. And within that volume lies not only all the matter and energy we can see, but all the structure that makes up the cosmos, from stars and galaxies to clusters and filaments emerging and evolving under the inexorable influence of gravity. To weigh the universe, then, is not merely to count stars or some particles. It is to measure the full story of cosmic energy in all its forms, to understand how the vacuum itself contributes to the architecture of the cosmos, and to confront the greatest mysteries that theoretical physics has yet to solve. Why does the vacuum weigh so little? Why is the cosmological constant not immense? And what principle of nature carved such an exquisitely balanced universe, one vast enough to grow old, stable enough to form galaxies, and gentle enough to allow us to ask at last just how much it weighs? The nullpunkt's energy. What is the true nature of empty space? Could the vacuum itself, seemingly so inert, so devoid of structure, conceal an energy so immense it challenges the very survival of the universe? To begin unraveling this mystery, we must return to a moment nearly a century ago to the vibrant city of Hamburg, a beacon of intellect and science in post-war Germany. There, in a modest cafe overlooking the tranquil waters of the inner Ulster, two physicists, friends, and colleagues shared a conversation that in hindsight stood at the precipice of one of the greatest cosmological enigmas of our age. Otto Stern, a cultured man with a passion for good wine and better company, leaned in to make his case. He was animated, brandy in hand, eyes bright with conviction. His friend across the table, Wolfgang Pauli, bore a fading black eye, the remnants of a barroom scuffle in Hamburg's raucous St. Pauli district. Though their temperaments diverged, Stern, the affable bon vivant Pauli, the volatile iconoclast, they were united in their pursuit of physics at its most fundamental. That day, they debated a concept now known to us as the vacuum energy, or, in German, the Nullpunktsenergie, the zero-point energy. Stern argued from observation, invoking data from the vapor pressures of neon isotopes. The discrepancy he calculated could not be reconciled without invoking the subtle presence of this ever-present energy, lurking even in the absence of matter. Pauli, characteristically skeptical, countered with a stark warning. If the Nullpunktsenergie truly existed in the quantity that quantum theory implied, it would have profound gravitational consequences. The universe, he claimed, wouldn't extend beyond the distance from Earth to the Moon. It would collapse upon itself under the weight of its own vacuum. This disagreement, passionate, personal, and profound, marked one of the earliest acknowledgments of a paradox that continues to confound physicists to this day. The idea that empty space might contain energy wasn't new. As early as 1911, Max Planck had speculated about zero-point fluctuations, suggesting that even in the absence of all matter and heat, a residual energy might remain. A few years later, Walter Nernst took the bold step of proposing that this energy might pervade all of space, an all-pervasive invisible sea of latent potential. Yet, it was Albert Einstein who introduced a separate but ultimately related concept, the cosmological constant, a term added to his general theory of relativity in 1917 to balance the gravitational pull of matter and achieve a static universe. Einstein's relationship with these ideas was complicated. Initially, he supported the cosmological constant as a mathematical necessity. He even collaborated with Stern to estimate the impact of zero-point energy on hydrogen molecules, but he failed to connect the two concepts. as observations revealed that the universe was not static but expanding. Einstein famously recanted his cosmological constant, referring to it allegedly as his biggest blunder. Likewise, he distanced himself from zero-point energy, deriding its mention with a self-deprecating smirk. But time would show that both the constant and the vacuum energy were far more than mathematical curiosities. They were central to the workings of our universe. The turning point came in the 1920s as quantum mechanics rose from the mathematical mist. On the island of Helgoland, beset by allergies and insomnia, Werner Heisenberg wrestled with the spectral lines of hydrogen atoms. There, amidst the dunes and salty air, he formulated what would become the uncertainty principle, an insight into the intrinsic unpredictability of nature at the smallest scales. Heisenberg's principle asserted that certain pairs of physical properties like position and momentum could not be simultaneously known with arbitrary precision, and from this the idea of zero-point energy naturally followed. If a particle could never be precisely at rest, then even in its lowest energy state it must possess some residual motion, some irreducible energy. To visualize this, imagine placing a marble in the bottom of a smooth bowl. In the classical view, it settles motionless at the lowest point, its energy fully expended, but in the quantum world such rest is forbidden. To know its position exactly would require complete ignorance of its momentum. Therefore, even at absolute zero, the marble must jiggle, however faintly. That jitter, imperceptible though it may be, corresponds to a real energy. Now, replace the marble with a subatomic particle, and the bowl with a quantum field. What you discover is that the vacuum itself can never be truly still. It writhes with fluctuations, virtual particles forever appearing and vanishing in a foam of probabilistic activity. These aren't particles in the traditional sense. They cannot be touched, weighed, or isolated. They don't leave direct tracks in detectors, but their effects are real. These vacuum fluctuations give rise to measurable forces. The Casimir effect, discovered by Dutch physicist Hendrik Casimir, is a striking example. When two uncharged metal plates are brought close together in a vacuum, they experience an attractive force not from electromagnetic interactions, but from the change in vacuum energy between them. This force is real enough to be measured. It even plays a role in the ability of geckos to cling to walls through the subtle van der Waals forces that arise from quantum vacuum effects between molecules. So, if vacuum energy is real, and if it can produce measurable forces, how much of it is there? This is where the problem begins. Physicists like Pauli attempted early estimates by partitioning space into tiny boxes. Imagine dividing a coffee cup of vacuum into infinitesimal regions, each allowed to contain virtual particles with energy limited by the uncertainty principle. Using the best resolution of their time, Pauli and his contemporaries imagined a cutoff scale around a femtometer, the approximate size of a proton. Even at this conservative scale, they found a staggering amount of energy in empty space, enough in a single coffee cup to boil away all the oceans of Earth. Fast forward a century, and we have probed much deeper into the quantum realm. With the Large Hadron Collider smashing particles together at near light speed, we can now resolve distances 100,000 times smaller than a proton. If we use these more refined scales in our vacuum energy calculations, the numbers spiral out of control. The energy density becomes so immense that a coffee cup of empty space could vaporize entire planets, indeed, entire galaxies, again and again. Go further still down to the Planck scale, the smallest scale at which space and time still retain meaning, and the energy becomes truly catastrophic. At this scale, a single coffee cup of vacuum could contain enough energy to obliterate all matter in the observable universe a trillion times over. And yet, paradoxically, we see none of this space, for all its emptiness behaves gently. The expansion of the universe is slow. Measured, delicate galaxies drift apart. Yes, but the very fabric of space is not heaving under the unimaginable weight of vacuum energy. The catastrophic predictions of theory are not reflected in reality. This is the essence of the cosmological constant problem. You see, in general, relativity, gravity, is not a force in the traditional sense. It is geometry. Energy and mass tell space. How to curve in curved space tells matter how to move. All forms of energy contribute to this curvature, not just matter but also light radiation and crucially vacuum energy. If vacuum energy is indeed as large as quantum field theory predicts, then its gravitational influence should be overwhelming. The curvature it imposes on space-time should be so extreme that the universe would not just collapse, it would never have emerged in the first place. There would have been no stars, no galaxies, no time for atoms to form or life to arise. The cosmos born a super heavyweight would have folded in on itself in an instant. But we are here. The universe exists. The observable cosmos stretches 47 billion light-years in every direction. It is filled with stars, planets, life, and the slow unfolding of time. Somehow, the vacuum energy we measure through observations such as the acceleration of cosmic expansion is not large. It is minuscule. It is 120 orders of magnitude smaller than what theory predicts. That discrepancy, a factor of 10^120, is the largest known between theory and observation in all of physics. It is not a minor oversight. It is a yawning chasm, a crisis. So what might resolve this paradox? Some have speculated that there is a mechanism currently unknown that cancels the vacuum energy almost perfectly, leaving just a tiny residual effect. Others have turned to the anthropic principle, arguing that we observe a small cosmological constant because universes with larger values would collapse too quickly for observers like us to evolve. In this view, the multiverse, a landscape of infinite universes, each with its own physical constants, might explain why we find ourselves in a universe so finely tuned for life. And there are those who suggest that we have misunderstood gravity itself. Perhaps general relativity, elegant though it is, fails to account for the true interaction between quantum energy and space-time curvature. Maybe a new theory, a quantum theory of gravity, will one day reveal a hidden structure that tames the vacuum and explains why its energy doesn't wreak havoc on the cosmos. Until then, the nullpunkt's energy remains a mystery, both tantalizing and terrifying. It whispers to us from the vacuum, hinting at hidden depths, inviting us to reconcile the elegance of quantum mechanics with the curvature of the cosmos. It is the silent architect of the cosmological constant problem, and it is a problem that demands our attention, not merely as a matter of scientific curiosity, but as a profound clue to the architecture of reality itself. In the end, what Polly and Stern debated over their coffee in Hamburg was more than academic. It was a glimpse into the abyss, the recognition that beneath the surface of what we call empty space lies a storm of quantum unrest, a surging sea of possibility whose true weight we still struggle to comprehend. The universe, it seems, is far more fragile and far more finely tuned than we ever dared to imagine. The cosmological constant problem. In the early autumn of 1949, a seemingly innocuous observation from a weather reconnaissance flight would mark a turning point in global history. A filter paper aboard a U.S. weather plane flying its usual route from Japan to Alaska registered an anomalous spike in atmospheric radioactivity. The filter was dispatched to Los Alamos for further analysis. There, the results were decisive. On September 23rd, President Harry Truman publicly confirmed that the Soviet Union had detonated its first atomic bomb. The nuclear arms race had begun. Beneath the shock waves of this geopolitical shift lay another moment of historical significance, perhaps less immediate in its consequence, but far more enduring in its reach. Just south of the explosion site at Semipalatinsk, Kazakhstan, 8 men sheltered in a trench observing the dawn of the Soviet nuclear era. Among them was Yakov Zeldovich, a towering figure in theoretical physics and head of the Soviet Union's nuclear theory division at Arzamas-16. Zeldovich's contributions to his nation's atomic program were immense, and within Soviet scientific circles he was revered. Yet his intellect extended far beyond the confines of weapons development. He was one of the rare physicists who could effortlessly traverse the frontiers of particle physics, general relativity, astrophysics, and cosmology. 2 decades after witnessing that terrifying mushroom cloud, Zeldovich would play a pivotal role in illuminating one of the most profound and unresolved enigmas in modern theoretical physics: the cosmological constant problem. By the late 1960s, the theoretical frameworks of the 20th century had achieved a remarkable level of maturity. Einstein's general theory of relativity had been tested against the precision of astronomical data and emerged victorious. It redefined gravity not as a force, but as the curvature of space-time caused by the presence of energy and momentum. Meanwhile, quantum field theory had become the dominant lens through which physicists viewed the subatomic world, a powerful amalgam of quantum mechanics and special relativity that described particles as excitations of underlying quantum fields. And yet, when Zeldovich brought these 2 towering pillars together, he encountered a contradiction so severe that it threatened the internal consistency of the entire edifice of theoretical physics. Zeldovich recognized that the vacuum of space, far from being a passive void, should be a dynamic and turbulent arena, one populated by incessant fluctuations of quantum fields, spawning virtual particles that blinked into and out of existence at unimaginable frequencies. According to quantum field theory, these ephemeral ripples carry energy, but in Einstein's theory, energy in all its forms curves space-time. Therefore, the vacuum itself should act as a gravitational source. It should bend the very shape of the universe. But if this vacuum energy, the so-called nullpunkts energy or zero-point energy, really existed in the amounts predicted by quantum theory, its gravitational impact would be catastrophic. Zeldovich calculated that the vacuum energy predicted by quantum field theory should curve space-time so violently that the universe would collapse into a singularity before atoms, stars, or galaxies had a chance to form. In his own words, clarifying the magnitude of the problem would carry tremendous fundamental significance for our understanding of nature. Here was a paradox that placed 2 of physics' most successful theories in direct conflict. Of course, this tension was not entirely new. Wolfgang Pauli, decades earlier in the 1920s, had pondered the gravitational consequences of vacuum energy. In a famous anecdote from a cafe in Hamburg, Pauli purportedly estimated the gravitational influence of the nullpunkts energy and concluded that a universe endowed with such energy could not even extend as far as the moon. His calculation, more intuitive than precise, was dismissed by some as fanciful. Yet Zeldovich, working with the more refined tools of post-war theoretical physics, reached a similar but far more rigorous conclusion, and he made the scientific community take notice. So, how do we reconcile this prediction with the universe we observe? After all, our universe is vast and ancient. It stretches 93 billion light-years across in every direction, and it has hosted galaxies, stars, planets, and life for over 13 billion years. If quantum field theory insists that empty space contains an immense, even infinite energy density, why hasn't this energy obliterated the cosmos? This is the cosmological constant problem, and it remains one of the most significant open questions in theoretical physics. On one hand, quantum field theory predicts a staggeringly large vacuum energy. On the other hand, observational cosmology, particularly measurements of the accelerating expansion of the universe, tells us that the actual energy density of the vacuum is small, very small. About 120 orders of magnitude smaller than the value predicted by naive calculations from quantum field theory. It is this discrepancy, sometimes described as the worst theoretical prediction in the history of physics, that demands an explanation, and the stakes are enormous. Resolving this conflict would likely require a radical reimagining of the fundamental principles that govern the universe. One school of thought advocates for a purely empirical approach. Ignore the theory, trust the data. If observations tell us that the vacuum energy is small, then so be it. Perhaps quantum field theory, despite its extraordinary success in describing particle physics, is simply inadequate at describing the vacuum structure of the universe. Yet, this route offers little comfort to those searching for a unified theory of nature. It amounts to giving up on our best theoretical tools, just because they yield the wrong answer. Scientists, by their nature, are not content with that. And so the search continues. Theoretical physicists have proposed a wide range of ideas over the past half-century. Some argue that vacuum energy from quantum fields must be counterbalanced by contributions from other, as yet undiscovered sectors of the universe. Perhaps there exists a new field or mechanism that cancels out the enormous contributions predicted by known particles. But for such a cancellation to yield a net energy density as small as what we observe would require a precision of 1 part in 120, a level of fine-tuning that borders on the absurd. It is like balancing the mass of a trillion suns against an equal weight accurate to the mass of a single electron. Others have taken a more radical path. One of the most controversial yet tantalizing ideas involves the multiverse. According to this view, our universe is just one of many, perhaps an infinite number, each with its own physical laws, constants, and vacuum energies. In most of these universes, the vacuum energy is either too large and positive, blowing the cosmos apart before galaxies can form, or too large and negative, collapsing it in a catastrophic big crunch shortly after birth. But in a tiny subset of these universes, the vacuum energy happens to fall within a narrow range, compatible with structure formation and eventually life. This is the anthropic argument. We find ourselves in a universe with a small cosmological constant, not because it had to be that way, but because we couldn't exist in a universe where it wasn't. The vacuum. Energy may well be a random parameter drawn from a vast ensemble of possibilities. The string theory landscape, as it is known. Depending on how one counts, this landscape might contain as many as 2,500 or even 10 to 7,000 possible vacuum states, each with a different value for the cosmological constant. In this picture, the problem is not why the vacuum energy is so small, but rather why it is small enough for us to be here asking the question. This line of reasoning has both defenders and critics. Some physicists, like Nobel laureate Steven Weinberg, have shown that the anthropic approach can make testable predictions. In the late 1990s, Weinberg and his collaborators argued that if dark energy, the observational manifestation of the cosmological constant, constituted less than 60% of the total energy density of the universe, the anthropic explanation would be invalid. But observational data from distant supernovae soon confirmed that dark energy accounts for about 70% of the universe's energy budget, thus passing this predictive hurdle. Still, many theorists are uneasy with anthropic reasoning. They argue that it undermines the predictive power of science. If any observed value can be explained post hoc by appealing to selection effects in an unobservable multiverse, then what becomes of falsifiability, the bedrock of the scientific method? In the meantime, Other speculative ideas continue to surface. Concepts such as vacuum energy, sequestering supersymmetric large extra dimensions, or modified theories of gravity offer alternate routes to solving the cosmological constant problem. Yet, none has emerged as a definitive solution. The problem remains stubbornly unsolved. What is clear is that this mystery lies at the heart of our quest to understand the universe. It is a deep wound in the otherwise elegant framework of modern physics. The cosmological constant problem is not merely an error to be corrected. It is a signpost pointing toward a more profound theory, a missing piece of the cosmic puzzle. It is deeply ironic that the substance causing us so much confusion is nothing at all empty space, or rather what we once thought was empty. We now know the vacuum is anything but empty. It is a seething, energetic ocean, bubbling with virtual particles and quantum fluctuations, and yet its energy density is almost imperceptible, so small that a coffee cup of vacuum holds less energy than it takes to swat a fly. So small that it has allowed the universe to expand slowly to grow old, to form galaxies, stars, planets, and ultimately life. And so, we return to where we began. We set out to weigh the universe. We measured the masses of stars and galaxies, the halos of invisible dark matter, and the faint glow of the cosmic microwave background. We measured the vacuum itself. And what we found was not a crushing burden, but a delicate balance. A cosmos surprisingly light, improbably gentle. A universe that should not have existed and yet does. And so, the question remains. Why is the vacuum energy so small? Why hasn't the universe been destroyed by the weight of its own empty space? What is the true nature of the nullpunk's energy? These are not just questions for physicists. They are questions about existence itself, about why the universe looks the way it does, about why we are here at all.
What happens to a theory when the world moves on? Where do discarded ideas go when the last believer is gone? Can something sound brilliant and still be completely, utterly wrong? Science is often seen as a shining staircase, each step bringing us closer to truth. But that staircase is littered with abandoned scaffolds and crumbling concepts, each one once thought to be the key to understanding everything. One man who knew this all too well was Wolfgang Pauli, a physicist of dazzling intellect, but also of razor-sharp critique. Known for skewering sloppy theories with his legendary wit, he famously dubbed one young physicist's paper not incorrect, but not even wrong. A verdict so damning, so final, it left no room for redemption. And yet, most scientific theories don't need a Pauli to end them. Time does the work just as well. They fade, quietly. Once celebrated, once taught in lecture halls and scribbled across blackboards, now only ghosts in old textbooks. Take phlogiston, for example, once believed to be the essence of fire, the invisible substance released when things burned. For a time in the 18th century, it was the cornerstone of chemistry. But phlogiston never existed. It was a fiction, eventually replaced by the rise of real chemistry and atomic theory. Somewhere in history, the last scientist who truly believed in phlogiston passed away, and with them, the idea vanished. Or consider the great cosmological rivalry of the 20th century, the Big Bang versus the steady state. One spoke of a hot, dense beginning, the other of an eternal, unchanging cosmos, forever replenishing itself. For a while, both vied for supremacy. Even Einstein gave the steady state some thought. But the universe had other plans, and it was quasars, cosmic relics from the early universe, that whispered the truth. Slowly, the steady state flickered out. Today, a new frontier looms. We now chase the deepest of all mysteries, the unification of quantum mechanics and general relativity. Our best contenders? String theory and M theory, dizzying frameworks of hidden dimensions, vibrating filaments, and, multi-dimensional brains. Conferences buzz, blackboards fill. Generations of physicists devote their lives to the dream. But the question remains, will these theories stand the test of time? Or will they too become footnotes, remembered not for what they explained, but for what they failed to become? Are they, in the end, not even wrong? The 5 string theories, a journey to the edge of fundamental reality. What does it mean for something to be fundamental? In physics, this term carries profound weight. It refers not simply to the smallest or most indivisible entities, but to the foundational principles and structures upon which all physical phenomena rest. To investigate this notion, let us embark on a conceptual journey inward, a voyage through the scales of physical reality, from the familiar world of humans, down to the potential bedrock of existence. Begin with our cells, bipedal members of Homo sapiens sapiens, typically standing just over 1.5 meters tall. This is our everyday scale, the anthropocentric reference point from which we measure the universe. Now, imagine compressing our field of vision by orders of magnitude. First, we descend to the scale of insects, small segmented organisms whose bodies span roughly 1 centimeter. This is a 100-fold reduction in scale. Zoom further to the cellular level. Cells, the fundamental units of biological life, typically measure a few micrometers in diameter, another factor of 10,000 smaller. At this level, we begin to glimpse the engine room of biology, mitochondria humming with chemical reactions, membranes orchestrating life's boundaries, DNA encoding the instructions of our form. But we do not stop there. Descend again by a factor of 1,000, and we reach the realm of molecules and atoms. Here, quantum mechanics begins to dominate. At distances on the order of nanometers and angstroms, less than a billionth of a meter, we see atoms bound by electromagnetic forces, electron orbitals shaping the geometry of molecules. The classical world begins to dissolve into a probabilistic fog. Continue inward. At the center of each atom lies the nucleus, a structure itself another 100,000 times smaller than the atom. Composed of protons and neutrons, each made up of even smaller constituents called quarks, the nucleus is held together by the strongest known force in nature, the aptly named strong nuclear force. This force binds quarks into nucleons, and nucleons into nuclei, operating at the scale of 1 femtometer, a million billionth of a meter. At this stage, we enter the domain of particle physics. The instruments we use to explore such minuscule realms, particle accelerators like the Large Hadron Collider, are among the most ambitious feats of human engineering. These colliders allow us to smash particles together at near light speeds and observe the fleeting traces of the fundamental forces at work. Through them, we can probe distances down to a few hundred atometers. But even the most powerful colliders yield to a barrier, the so-called Planck length. The Planck length, approximately 1.6 times 10 to the negative 35 meters, is theorized to represent a limit beyond which our current understanding of space and time ceases to apply. At this scale, general relativity, the elegant theory of gravity developed by Einstein, must confront the probabilistic chaos of quantum mechanics. It is here that physicists believe a new framework is required, a theory of quantum gravity. Enter string theory. String theory proposes that the ultimate constituents of matter are not point-like particles, but one-dimensional vibrating entities called strings. These strings oscillate at different frequencies, giving rise to the properties of particles, mass, charge, spin, as emergent phenomena of their vibration modes. According to the theory, strings may be either closed loops or open strands, and they exist not just in the familiar 4 dimensions of space-time, but in a higher dimensional space, often with 10 or 11 total dimensions, compactified in ways we cannot yet observe directly. Paradoxically, string theory was not originally conceived as a theory of everything. It began its life as a speculative model of the strong nuclear force. In 1968, a groundbreaking paper by Gabriele Veneziano introduced a mathematical formula that astonishingly matched experimental results for particle scattering. This formula hinted at an underlying string-like structure, and soon, theorists envisioned protons and neutrons as composed of vibrating strings rather than point particles. Excitement surged. The community paused, captivated by the beauty of the equations and their unexpected accuracy. For a moment, it seemed string theory might offer a unified description of nuclear interactions. Yet, the joy was short-lived. Experiments in the early 1970s revealed that protons and neutrons do not behave as expected under high-energy collisions if they were string-like. Rather than deforming and scattering softly, like gelatinous blobs, their behavior more closely resembled billiard balls rebounding with sharp impacts. The predictions of string theory were inconsistent with reality. By 1973, the theory was discarded as a candidate for explaining the strong force. In its place rose quantum chromodynamics, a successful and experimentally validated theory based on the exchange of gluons between quarks. String theory, it seemed, was dead. But in theoretical physics, intellectual death often precedes conceptual resurrection. Some researchers, most notably John Schwarz and Michael Green, recognized peculiar features in string theory that seemed too elegant to be coincidental. Among these was the natural incorporation of a particle with the properties of the graviton, a hypothetical quantum of gravity. Moreover, anomalies that typically rendered quantum theories inconsistent canceled out in string theory, but only in specific dimensions. In particular, string theory appeared consistent only in 10-dimensional spacetime, with 9 spatial dimensions and 1 temporal. Throughout the 1980s, these findings culminated in what is now called the first superstring revolution. String theory was reborn, not as a model for the strong force, but as a contender for the long-sought quantum theory of gravity. It promised not only to unify general relativity and quantum mechanics, but also to incorporate all other known forces, electromagnetic, weak, and strong, into a single framework. Physicists dared to dream. Perhaps string theory was the ultimate blueprint of reality. But then came an unexpected twist. Instead of a single elegant theory, string theorists uncovered 5 distinct and mathematically consistent string theories. Each operated in 10 dimensions and included supersymmetry, a symmetry that pairs bosons and fermions, but differed in key structural elements. The 5 theories are: Type 1, incorporating both open and closed strings. The presence of open strings allows interactions that resemble the electromagnetic, weak, and strong forces, while closed strings mediate gravity. Type 2a, a theory of closed strings with non-chiral supersymmetry, where the left and right moving vibrations on the string are symmetric. Type 2b, also involving only closed strings, but with chiral supersymmetry, distinguishing left and right moving modes. Heterotic SO32, a hybrid theory that combines left-moving strings from a bosonic theory with right-moving strings from a supersymmetric one, possessing a gauge symmetry group of SO32. Heterotic E8 times E8, similar to the above, but with a different gauge symmetry group. This version became especially prominent in attempts to relate string theory to observable particle physics. These theories differ in the types of strings they permit, the nature of supersymmetry they exhibit, and the symmetries of their internal spaces. Yet all are internally self-consistent. 5 logically distinct, yet viable theories, all in 10 dimensions, all incorporating gravity, and all arising from the same conceptual framework. For physicists seeking a unique and singular theory of everything, this proliferation was troubling. 5 is not 1. Even 2 would have been one too many. Was nature indecisive? Or were these seemingly separate theories different perspectives on a deeper, unified structure? This puzzle set the stage for the second superstring revolution of the mid-1990s, which introduced the concept of duality. Dualities are mathematical transformations that show how two apparently different theories are in fact equivalent when viewed from different vantage points, such as strong versus weak coupling, or small versus large compact dimensions. Through these dualities, the 5 string theories were shown to be interconnected, like the faces of a single multidimensional object. Moreover, an even more fundamental framework emerged, M-theory, which suggested that all 5 string theories are simply different limits of a more profound, 11-dimensional theory. In this view, strings are just one-dimensional slices of higher-dimensional objects known as branes. The journey inward, begun as a search for the smallest building blocks of matter, now touches the outer edges of a new conceptual frontier. String theory, with its promise and its puzzles, may not yet be the final answer. But it has reshaped the questions. In seeking the fundamental, we discovered that even the search for unity is a multifaceted endeavor, where the most profound truths may come not in solitary whispers, but in the harmonized vibration of many strings. One theory to rule them all, the emergence of M-theory. In an ancient Indian parable, a group of blind men encounter an elephant for the first time. Each man reaches out to touch the creature and describe what he feels. One grasps the trunk and declares it must be a serpent. Another touches the leg and likens it to a tree trunk. A third, feeling the tusk, proclaims it a spear or some war machine. Individually, their observations are coherent. Collectively, they are incomplete. None can perceive the full reality of the elephant. And so, each mistakes a fragment for the whole. This parable, though simple, captures something profound about the nature of scientific inquiry, particularly the development of string theory in the latter half of the 20th century. By the mid-1980s, physicists had formulated 5 distinct yet mathematically consistent string theories, each offering a candidate for the unification of gravity with quantum mechanics. And yet the existence of 5 such fundamental theories posed a deep conceptual dilemma. Nature, it seemed, should be governed by a single, elegant framework. Were these 5 descriptions independent theories? Or could they represent different perspectives, partial glimpses of a deeper, more comprehensive structure? The answer would not fully emerge until 1995, when physicist Edward Witten unveiled a revolutionary new perspective that would forever alter the landscape of theoretical physics. What he proposed was startling in its ambition and coherence, that the 5 seemingly distinct string theories, along with an 11th dimensional gravitational theory known as supergravity, were merely boundaries, limiting cases of a single, unified framework. He called it M-theory. But before delving into Witten's breakthrough, it is worth revisiting the context from which M-theory arose. By the 1980s, string theory had matured from a failed model of the strong nuclear force into a leading contender for a unified theory of everything. It offered the tantalizing possibility of reconciling general relativity with quantum mechanics, a holy grail in theoretical physics. The theory posited that all fundamental particles were not point-like, but rather vibrational modes of tiny, one-dimensional strings. Yet there was a problem. Not 1, but 5 consistent string theories existed, each with unique properties. Type 1 contained both open and closed strings, with supersymmetry between fermions and bosons. Type Ia and Type Ib both involved only closed strings, but differed in their chirality. how left and right moving string modes behaved. Heterotic SO32 and heterotic E8 times E8, hybrids combining bosonic string modes on one side and supersymmetric modes on the other. Each theory existed in 10 dimensions and accommodated gravity through a massless spin-2 particle, identified with the graviton. But 5 fundamental theories? That was philosophically unsettling. As physicists, we seek unity, not multiplicity. If the universe is governed by a single set of physical laws, why should there be 5? The theories were too similar to be entirely independent, yet too different to be trivially equivalent. Like the blind man and the elephant, theorists suspected they were glimpsing only pieces of a deeper whole. The challenge was to find the coherent object they all described. Edward Witten was not always destined for theoretical physics. His academic journey began in history, and for a time, he even contemplated a career in politics. Yet his intellectual curiosity led him through economics and eventually into the realm of high-energy theoretical physics. What distinguished Witten was not merely his brilliance, but his fluency in 2 often disparate languages, mathematics and physics. Where physicists value physical intuition and conceptual flexibility, mathematicians prioritize rigor and precision. Witten bridged this divide with ease. By 1995, Witten had already transformed multiple fields, topological field theory, supersymmetry, and string theory among them. His work had earned him the Fields Medal, the most prestigious award in mathematics, making him the first and only physicist to do so. So when he stood before a packed audience at the Strings 95 conference at the University of Southern California, the room was electric with anticipation. Then came the revelation. The 5 10-dimensional string theories and 11-dimensional supergravity were not distinct theories at all. They were different approximations, limiting cases of a single, more fundamental theory. This theory, which had yet to be fully formulated, Witten dubbed M-theory. Witten's analogy was compelling. Imagine a vast, unknown continent. On its periphery lie 5 coastal cities: Sydney, Adelaide, Perth, Darwin, Brisbane. Each city is unique, but all belong to the same underlying landmass. M-theory was the continent. The 5 string theories were its cities, situated at different boundaries. Supergravity was another outpost on this landscape. Between them stretched an interior, unexplored, complex, and rich with terrain, connecting each apparent theory into one unified whole. In technical terms, these connections were made possible by dualities, symmetries that relate seemingly distinct physical theories. Some dualities relate strong coupling to weak coupling. Others relate large spatial dimensions to small ones. These dualities suggested that what looked like separate theories were actually the same theory viewed from different physical regimes. But M-theory offered even more. It required 11 dimensions, not 10. This was surprising, since string theories had been developed explicitly in 10 dimensions. Yet the addition of one extra spatial dimension opened up new mathematical structures and fundamental objects beyond strings. Strings, Witten proposed, were not the most basic constituents of the universe. They were merely one-dimensional projections of higher-dimensional entities called branes. The word brain is derived from membrane, and it generalizes the idea of an extended object. A one-brane is a string. A two-brane is a membrane, a two-dimensional surface. A three-brane has 3 spatial dimensions, and so forth. Theoretically, M-theory accommodates branes of various dimensionalities embedded within an 11-dimensional spacetime. To understand this, imagine a string stretched taut between 2 points. This is a one-brane. Now, imagine a soap film stretched across a wire loop. This is a two-brane. Though our minds falter at visualizing higher dimensions, the mathematics handles such entities with ease. crucially, brains under tension can wrap around small dimensions. If one of the 11 dimensions is compactified, curled up like a tiny circle, a two-dimensional brain could wrap around this circle. To a low-energy observer, it would appear as a vibrating one-dimensional string. Thus, in specific limits, M-theory reduces to string theory, and brains become strings. But in its full glory, M-theory is a higher-dimensional theory in which brains, not strings, are fundamental. But how can extra dimensions, let alone wrapped brains, be real when we do not see them? To answer this, physicists often invoke the metaphor of an ant walking along a garden hose. To the ant, the hose is a one-dimensional path. It can move forward and backward, but the hose also has a circular cross-section. If the ant were small enough, or if its feet were sensitive enough, it might detect the curled-up second dimension and walk around it. To us, however, the circular dimension is invisible. We are simply too large and imprecise. In the same way, string theory and M-theory posit that 6 or 7 extra spatial dimensions exist, but they are compactified, curled up so tightly that we cannot detect them with current instruments. These hidden dimensions could be shaped in elaborate geometric forms, such as Calabi-Yau manifolds, which influence the behavior of particles and forces we observe in our four-dimensional spacetime. Now add brains into this picture. Consider a two-brain wrapping around a tiny curled-up dimension, like shrink-wrap folding around a wire. The surface tension causes the brain to conform tightly to the shape it encloses, effectively reducing its dimensionality. This process, called dimensional reduction, is central to how higher-dimensional brains manifest as lower-dimensional strings or particles in our universe. Thus, what appears as a string in 10-dimensional spacetime might actually be a tightly wrapped brain from an 11-dimensional M-theory framework. The implications of M-theory extend far beyond technical unification. They touch on the structure of the cosmos itself. Our universe could, in this view, be a three-dimensional brain, floating in a higher dimensional bulk. Other brains might exist in parallel, perhaps containing entire universes with their own laws of physics. Moreover, the Big Bang might be reinterpreted as a collision between brains, cosmic objects crashing through higher dimensional space. Such ideas are speculative, yet mathematically plausible within the framework of M-theory. And so, the elegant simplicity of string theory yields to a richer and more mysterious vision of reality. A cosmos where dimensions, shapes, and extended objects intertwine in a higher dimensional dance. Where strings arise not as primordial threads, but as shadows cast by deeper, multi-dimensional forms. Witten's proposal in 1995 did not conclude the story. It opened a new chapter. Much about M-theory remains unknown. No complete formulation exists. We do not yet possess a full set of equations describing its dynamics. And yet, the coherence of its implications, the power of its unifying structure, and the elegance of its geometric underpinnings offer a tantalizing glimpse into a deeper order of nature. In the end, M-theory may not be the final theory, but it reveals the terrain upon which such a theory might be found. Like the blind men groping at the elephant, we may still be feeling our way through fragmented understandings. But the shape of the elephant, the great coherent structure, has begun to emerge from the shadows. Whether M stands for mystery, magic, membrane, or simply the next letter in the alphabet after L for limit, remains unresolved. Perhaps the true meaning of M-theory, like the theory itself, awaits discovery. One that will finally link the elegant mathematics of higher dimensional brains to the burning stars and expanding galaxies we observe in the night sky. Brain cosmology, dimensions beyond the horizon? Consider for a moment the surface of a still pond. At times, tiny insects, water boatmen or backswimmers, can be seen skimming effortlessly across it, bound to the thin surface tension that supports their weight. They neither sink into the depths nor soar into the open air above. Their world, for all intents and purposes, is two-dimensional. They exist confined to a membrane, seemingly unaware of the vast three-dimensional environment that surrounds them. What if we are similarly limited in our perception? This analogy, modest yet profound, captures the central premise of brain cosmology. Just as the pond's surface defines the observable world for those insects, our own universe might be a three-dimensional brain embedded within a higher dimensional space. This possibility arises naturally within the framework of M-theory, the proposed unifying theory of all fundamental interactions that encompasses and extends the ideas of string theory. Within M-theory, extended objects called brains, short for membranes, occupy central roles. M-theory predicts not only two-dimensional M2 brains, but also five-dimensional M5 brains. When these higher dimensional entities wrap around compactified dimensions, especially the extra 11th dimension proposed by N-theory and the 6 curled-up dimensions from string theory, some physicists hypothesize that they could effectively manifest as three-dimensional surfaces. Crucially, such brains could be vast enough to contain an entire universe. In this conception, our universe is not the totality of all that exists, but rather a slice within a grander, higher dimensional reality. The fundamental forces described by the Standard Model, electromagnetism, the weak nuclear force, and the strong nuclear force, may be confined to this brain, their field lines limited to the three spatial dimensions we observe. Like ripples across the pond, these forces remain bound to the surface, incapable of escaping into the wider bulk. Yet gravity behaves differently. Unlike the other interactions, gravity in this framework is not restricted to the brain. Instead, its force lines, or more precisely, the gravitational field described by the curvature of spacetime in general relativity, can propagate into the higher dimensional bulk. This leakage provides a compelling explanation for the long-standing puzzle of gravity's relative weakness. The electromagnetic signals in your nervous system are powerful enough to lift a pen against the gravitational pull of the entire Earth, which weighs approximately 6 times 10 to the power of 24 kilograms. This extraordinary discrepancy in strength may be due to gravity's dilution across extra dimensions. While the other forces remain tightly localized to the brain, gravity spills into the higher dimensional space, weakening its apparent strength in our familiar three-dimensional world. Thus, brain cosmology offers a framework where the forced hierarchy problem, the striking difference in strengths among the fundamental forces, emerges not as an anomaly, but as a natural consequence of dimensional geography. But brain theories do more than address gravity. They have also been invoked in bold attempts to explain the origin and evolution of the universe itself. In some models of the early cosmos, brains play a dynamical role, moving and interacting within the higher dimensional bulk. One such scenario is known as brain inflation. Here, the inflationary epoch, a brief but astonishingly rapid expansion of space, believed to have occurred fractions of a second after the Big Bang, is driven not by a hypothetical scalar field, but by the motion and tension of brains. The tension associated with brains, immense in magnitude, could drive a repulsive gravitational effect, accelerating the expansion of space. As the brain traverses the bulk, this motion corresponds to the inflationary dynamics observed in cosmology. In this vision, the birth of the universe is not merely a singular explosion from nothing, but a grand unfolding of higher dimensional geometry. An even more provocative model is the ekpyrotic scenario, in which the Big Bang is reinterpreted not as a beginning, but as a transformative event, a collision between brains. In this picture, a neighboring brain in the bulk approaches and collides with our own. The energy released in the collision seeds the universe with perturbations, slight irregularities, that, under the influence of gravity, evolve into the large-scale cosmic structures we see today. Galaxies, clusters, and filaments stretching across the observable universe. Such ideas are nothing short of extraordinary. They challenge the traditional narrative of cosmology and reframe our understanding of space-time. But they also demand an essential question. Why take these speculative constructions seriously? Why entertain the notion of invisible dimensions and unseen brains unless we have reason to believe they reflect reality? This is where brain cosmology meets a fundamental challenge of modern theoretical physics, the chasm between mathematical elegance and empirical validation. Every theoretical physicist eventually encounters a peculiar ritual, a thick envelope containing a self-published manuscript, usually accompanied by a handwritten letter declaring the discovery of a new theory of everything. Often, the writer claims to have corrected Einstein's errors. The contents, while passionate, are a morass of undefined symbols and disconnected assertions, a patchwork of ill-formed equations that fail even the most basic standards of logical coherence. As the physicist Wolfgang Pauli once quipped, such ideas are not even wrong, not simply incorrect, but lacking the internal structure required to be evaluated meaningfully. And this concern is echoed by skeptics of string theory and M-theory alike. Are these frameworks, so intricate, so beautiful, more than mathematical artistry? Are they themselves not even wrong, elaborate constructs without experimental anchor? There are, in truth, two notions of correctness at stake. The first and ultimate is empirical. Does the theory describe the real universe? Does it make testable predictions that can be verified by experiment or observation? In this regard, string theory and its extension into M-theory face formidable obstacles. As of today, there is no direct experimental evidence confirming any aspect of string theory, extra dimensions, or brains. Probing these regimes would require energies vastly beyond our technological reach. To appreciate the scale of this challenge, consider that the Large Hadron Collider, the most powerful particle accelerator built by humanity, reaches energies on the order of 10 to the 13 electron volts. Yet the energies required to probe string-scale physics are thought to lie around the Planck scale, approximately 10 to the 19 electron volts. A factor of 100 billion beyond current capabilities. Building an accelerator to reach such energies using present-day methods would require a ring extending well beyond Earth, perhaps as far as the orbit of Mercury. Such a project is for now a dream beyond engineering or economic plausibility. But there is a second, subtler sense of correctness: mathematical consistency. Even in the absence of experimental data, a theory can be evaluated based on its internal logic, its coherence, and its compatibility with known physics. Here, M-theory and brain cosmology fare better. They are built atop decades of cumulative progress in quantum field theory, general relativity, and topology. Concepts like perturbative finiteness, dualities, and supersymmetry are not merely jargon. They are essential mathematical properties that constrain the behavior of the theory in precise ways. Still, understanding these ideas demands deep expertise. From the outside, theoretical physics can resemble a linguistic battle of arcane terminology. How can one distinguish between an idea that is wrong and one that is simply misunderstood? When can we be sure that a theory is truly internally consistent and not merely elusive? Ultimately, in the absence of experimental access, physicists must cultivate a hybrid approach, balancing creativity with rigor intuition with proof. Brain cosmology remains a speculative domain, but it is not arbitrary. It is shaped by an intense interplay between mathematics and physical reasoning, between bold imagination and unforgiving scrutiny. So, are brains real? Is M-theory a true description of nature or an elegant mirage? The answer is not yet known, but in the pursuit of such questions, physics performs its noblest function. It compels us to think beyond the visible, to question the familiar, and to imagine realities stranger and perhaps more beautiful than any we have yet observed. Proving the unprovable, duality, brains, and the deep structure of reality. Not far from the restless rhythm of New York City lies the hushed town of Princeton, home to ivy-covered walls and contemplative minds. Nestled at its outskirts, surrounded by forested serenity, stands the Institute for Advanced Study, an academic sanctuary unlike any other. Here, scholars are not encumbered by undergraduate lectures or lab supervision. Their currency is thought itself. The Institute has hosted some of the most luminous intellects in modern science. J. Robert Oppenheimer, the father of the atomic bomb, Freeman Dyson, architect of quantum electrodynamics, and perhaps most famously, Albert Einstein, who spent his final decades chasing the elusive dream of a unified theory. Einstein's later years were marked by a noble struggle to reconcile the forces of nature within a single framework, a quest that remained unresolved in his lifetime. Yet that ambition persists today. One of the Institute's contemporary torchbearers in this pursuit is the Argentinian theoretical physicist Juan Maldacena. Modest in demeanor, soft-spoken in delivery, Maldacena lacks the flamboyance often associated with revolutionary ideas. But in 1997, he proposed a theoretical framework so profound, it reshaped our understanding of gravity, space, and the very notion of dimensionality. At its core lies a correspondence known as ADAS-CFT, short for anti-de Sitter, conformal field theory correspondence. The name itself is unassuming, technical, even forgettable, but beneath it lies one of the most powerful insights born from string theory in the past 3 decades. To comprehend its implications, we must return to the physics of brains. Brains, short for membranes, are multi-dimensional objects that arise in M-theory and string theory. In this framework, particles are not fundamental point-like entities, but rather one-dimensional strings or higher-dimensional brains. Maldacena's insight stemmed from exploring how physical laws manifest for an observer positioned close to such a brain. He envisioned 2 perspectives. First, consider an observer who lives on the brain, a hypothetical being confined to the brain's surface, much like a water boatman skating across a pond. To this observer, the laws of physics are dictated by the interactions and fluctuations within the brain itself. These might resemble, in form and content, the quantum field theories we use to describe fundamental forces, such as the strong interaction. Now, contrast this with a second perspective, that of an observer residing in the bulk, the higher dimensional space in which the brain is embedded. To this external viewer, the brain is not merely a flat surface, but a gravitational entity curving the surrounding spacetime. The physics, from this vantage, is governed by a higher dimensional theory of gravity, one that incorporates the brain not just as a locus of tension, but as a dynamic source of curvature. Here was Maldacena's audacious proposition. Although the equations used by each observer, the one on the brain and the one in the bulk, appear entirely distinct, they describe precisely the same physical system. Every measurable quantity, every dynamic process, every correlation function that could be calculated in one description had a corresponding analog in the other. These 2 radically different formulations were, in fact, mathematically equivalent. This is what physicists call a duality, a concept that, like the Rosetta Stone, translates between two languages of physics. Just as ancient Egyptian hieroglyphs were deciphered by matching them with Greek and Demotic texts, a duality allows the same physical truth to be expressed through two dissimilar mathematical vocabularies. The ADS-CFT duality links a conformal field theory, a quantum field theory without gravity, living on a flat spacetime, with a gravitational theory defined in a higher dimensional anti-de Sitter space. It is a mapping from a four-dimensional world without gravity to a five-dimensional world with gravity, and crucially, the fifth dimension corresponds to the radial, vertical distance into the bulk spacetime, perpendicular to the brane itself. One of the most compelling validations of this duality comes from a specific calculation. Physicists, working within the conformal field theory, computed an extraordinarily precise result, a quantity involving gauge interactions and quantum fluctuations. The mathematical structure was deeply non-trivial, so complex, in fact, that it defied the possibility of random coincidence. Then, astonishingly, the same quantity was computed using the gravitational theory in 5 dimensions. The results matched perfectly. Such a match is not a fluke. It signals a profound truth. Two different paths through the jungle of equations lead to the same clearing. The 4-dimensional world of gauge theory and the 5-dimensional world of gravity, for all their surface differences, are shadows of the same deeper structure. But what does this mean physically? To appreciate the depth of Maldaceno's conjecture, one must understand a key feature of quantum field theories. Some are more quantum than others. In certain contexts, like the motion of a baseball or the trajectory of a planet, quantum effects are negligible. Classical physics it suffices. Gravity, in particular, is a weak force whose quantum corrections are often imperceptibly small. However, in other domains, especially those governed by the strong nuclear force, quantum fluctuations dominate. The theories used to describe these regimes, like quantum chromodynamics, are non-linear and intractable by ordinary perturbative methods. Maldaceno's duality flips this problem on its head. When the quantum field theory becomes strongly coupled and difficult to solve, its gravitational dual becomes weakly curved and easier to compute, and vice versa. In this way, gravity, often the most enigmatic force, becomes a tool to understand the least accessible regions of quantum field theory. It's as if two locked doors stand before us, one to the mysteries of gravity, the other to quantum fields. Maldaceno's correspondence hands us a key that opens both. At first, the idea was met with skepticism. Could it truly be that a theory of gravity in 5 dimensions was equivalent to a theory without gravity in 4? Could such a strange symmetry be more than a formal coincidence? But over time, rigorous checks, detailed calculations, and mounting evidence silenced many doubters. What began as a speculative conjecture evolved into a cornerstone of theoretical physics. Importantly, this duality does not yet imply that M-theory or any string theoretic model is the definitive description of our universe. We still lack direct experimental confirmation. The ADS-CFT correspondence is most rigorously understood in special geometries, such as ADS spaces, that differ from the de Sitter geometry believed to describe our expanding cosmos. Yet what we do know is significant. The mathematical structure of string theory, with its branes, dualities, and higher dimensional formulations, is not nonsense. It is consistent, coherent, and predictive within its domain. Even if nature has chosen a different path, this body of ideas reflects a logic that is internally harmonious and stunningly elegant. So, is this the end of the line? Have we reached the final frontier of physics? Or is it possible that the path continues, spiraling deeper and deeper into more abstract territories? Layers of reality, stacked like Russian dolls, each embedded within the next. We do not yet know. Perhaps at the heart of matter are vibrating strings and higher dimensional branes. Perhaps the universe is a hologram, with gravity emerging from quantum information encoded on lower dimensional boundaries. Or perhaps we are simply scratching the surface, our current models destined to be subsumed into grander syntheses. But this much is clear: the ADS-CFT correspondence and the web of dualities it reveals are not wild conjectures born of desperation. They are part of a robust theoretical edifice, one that hints at an underlying unity beneath the patchwork of known physics. It is an edifice built not on wishful thinking, but on rigorous mathematics, conceptual clarity, and a persistent search for truth. And so, in the woods of Princeton, in the quiet offices of the Institute for Advanced Study, the tradition continues. The drive to prove the unprovable is not hubris. It is a testament to the belief that reality, no matter how strange, is ultimately knowable. The equations may speak in many dialects, but their meaning, if we listen closely enough, remains one: